Hello, everyone. Last week we talked about process manager, processes, process states, following by different state diagrams, including the two-state model, five-state model, six-state model, and seven-state models. We have discussed different queuing models like the first come, first serve, shortest job first, and the priority queues. We have also uh, um, talked about dispatcher as part of the operating system to schedule the switching between processes and the different traces as path of execution of each process. So the agenda for today is to go over two parts. The first one is on operating system control tables, the process control structure, followed by the process control in terms of mode of execution, process creation, and process switching. We need to know how the process control is established within the operating system in terms of what kind of processor execution modes we will address, how the process creation is performed within the operating system, how the process switching is conducted. And then we will go over a case study using Unix SVR4 as an example to provide an accurate and a more detailed process management using a description of the process states, the process description, and the process control. So if the operating system is to manage processes and resources, we know that it must have information about the current state of each process and resource. The universal approach to providing this information is straightforward. The operating system must contain and maintain tables of information about each entity that it's managing. A general idea of the scope of this effort is indicated in this figure. In this figure, we see four different tables maintained by the operating system, including the memory table, the I/O table, the file table, and of course, the process table. And this week and maybe in the next week, a couple of weeks, we will still focus on process manager. So we will cover process management in more details using the notion of the process table maintained by the operating system. All of these details will be discussed in later classes, but in today's class, I would like to give a brief introduction about the memory table, I/O table, and file tables, in addition to more information about process management and control. Keep in mind that although the details will differ from one operating system to another, fundamentally all operating systems, they maintain information in these four tables or these four categories. So in memory tables, we primarily use these tables to keep track of both main memory and secondary or virtual memory. Some of main memory is reserved for use by the operating system, and the remainder is available for use by processes. Processes are maintained on the secondary memory. This is by using some sort of virtual memory or simpler swapping mechanism. The memory tables, they must include the following information. We must include information about the allocation of main memory to processes, the allocation of secondary memory to processes. Also, we need information about any protection attributes of blocks of main memory, or even virtual memory, such as which process may access certain shared memory regions. We also need any additional information needed to provide the full management of the virtual memory. And this mainly this table these tables are mainly used within the memory management system, and later on you will see cross reference between these tables and any other tables, whether it's on the IO management level or the file management level or even the process management level. So for the I/O tables, they are primarily used by the operating system to manage the I/O devices and the channels of the computer system. At any given time, an I/O device may be available or even assigned to a particular process. If I/O operation is in progress, what the operating system need to know you would need to know the status of the I/O operation as well as the location in the main memory that is being used at the source or even the destination of the I/O transfer. The following set of tables include file tables. The operating system may also maintain file tables. These tables provide information about the existence of file. It provides information about the location on the secondary memory, their current status, and other attributes. Much, if not all, of this information may be maintained and used by a file management system. That means the operating system has little or no knowledge of files. In other operating system, we might see that much of the detail of the file management is managed by the operating system itself. Finally, the operating system must maintain process tables to manage processes. The remainder of today's class will be devoted to the examination of the required process tables and management. And before proceeding to this discussion, two additional points should be made. First, we need to differentiate between the four tables and how each one of those tables are working on its own. And second, how these tables are linked or cross-referenced in some fashion. So memory, I/O, and file are managed on behalf of processes. So there must be some sort of reference to these resources directly or even indirectly in the process table. The files referred to in the file tables are accessed via an input-output device and will at some time be in the main or virtual memory. That's why the file tables and process table will always be cross-referenced, or there will be some reference between the tables. The table themselves must be accessible by the operating system and therefore are subject to memory management. So now let's consider what the operating system must know if it's to manage and control a process. First, it must know where the process is located. And second, it must know the attributes of the process that are necessarily used for managing such a process. Example like process ID, identifier, or even process state. In general, we refer to the process control block. Let's discuss each of those process control structure in more detail. Before we can deal with the questions of where the process is located or what attributes are assigned to each process, we need to address an even more fundamental question, which is, what is the physical manifestation of a process? Actually, as a minimum, a process must include a program or set of programs to be executed. Associated with these programs is a set of data locations for local and global variables and any defined constant. Thus, a process will consist of at least sufficient memory to hold the programs and data of that process. In addition, the execution of the program typically involves a stack, as we discussed before, that is used to keep track of procedure calls and parameter passing between processes. Finally, each process has its own associated number of attributes that are used by the operating system for control. So these attributes are the second control structure that we use it to primarily provide a full control and management to the operating system. And the location of the collection of program, data, stack, and attribute is referred to the process image. The process image location mainly depends on the memory management scheme that is used. In the simple case, the process image is maintained as a continuous block of memory. This block is maintained in a secondary memory, usually the hard disk, so that the operating system can manage the process. At least a small portion of the image of the process should be maintained in the main memory, And to execute the process, the entire process image must be loaded in the main memory, or at least virtual memory. So these are the fundamental control structures that we needed to process, to provide the control over processes by the operating system. It needs information about where the process is located, as well as process attributes. Thus, you can see at later stage how the tables that are maintained by the operating system are cross-referenced. So if we look to the typical elements of a process image, we see four components. We will refer to these components as um, user data, as we talked before, user program, and then process control block. And then when we add the stack into those three main process elements or process attributes, then we will call it a process image. So as we defined before, a user data is simply the modifiable part of the user space, which actually may include both program data, user stack area, and even programs that may be modified. A user program is simply the program to be executed in the stack. We store the parameters and the calling addresses for procedure and system calls. In the process control block, we do have all the attributes needed to define and to control the process, which we have addressed before. In providing more sophisticated multi-programming system, that would require a great deal of information about each process. And as was explained before, this information can be considered to reside in the process control block. Now, if we'd like to look into typical elements of a process control block, we know that different systems will organize this information in different ways. And several examples of this appear at the end of next week when we talk about different case studies. But for now, let's assume we will focus on a simple scenario where we explore the type of information that might be of use of an operating system. Without actually focusing on what type of operating system is, we just look fundamentally what are the main information or typical elements we can see it in a process control block within the process image, by which the operating system can provide full control on processes for management. So if we look in this tableau, we can see fundamental typical categories of information that are required by the operating system for each process. Somehow you may be surprised at the quantity of information required, because as you gain a greater appreciation of the responsibility of the operating system, you need to collect as much as you can in the process control block to make it more reasonable of a process management system in big system, or like even complex systems. So we can group the process control block information into three general categories. The first one is the process identification. The next one is the process state information, the processor state information, and the third one is the process control information. You can go over each of these tableaux in more details in the textbook. However, I'll provide you with some summarization as follow. With respect to process identification, as part of the process control block, in virtually all operating systems, each process is assigned a unique number, unique identifier, which may simply be an index into the primary process table. Otherwise, there must be a mapping. Why do we need those process identifiers? Because there must be a mapping that allow the operating system to locate the appropriate tables based on the process identifier. This identifier is used in several ways. Many of the other tables that are controlled by the operating system may use process identifier to cross-reference process tables. For example, the memory table may actually may be organized so as to provide a map of main memory with an indication of which process is assigned to each region. So at this point, we do need the process identifier for this purposes. Also, similar reference could be also appear in the I/O and even for the file tables. So when a process would communicate with other with one another or with other processes, the process identifier or the unique identifier for each process is merely used to inform the operating system about the source and destination of the communication. Also, when the processes are allowed to create another processes, like we need the process identifier to claim which process is a parent and which process is a child. So in addition to these process identifier, a process itself may be assigned a user identifier that would indicate the user responsible for a job. So as we talked about the process identifier and how it's an important component in the process control block, the second category of information that is mandatory to be involved in the process control block is the processor state information. The processor state information consists of the contents of the processor registers. While a process is running, of course, the information is in the registers. When the process is interrupted, all of this register information must be saved so that it can be restored when the process resumes execution. The nature and number of registers involved depend on the design of the processor. Typically, the register set will include user visible registers, control and status registers, and stack pointers. On a particular note, all processor designs include a register or set of registers, often known as the program status word, that contains condition codes plus status information. A good example of a processor status word is that on the Intel x86 processor, which referred to as the E flags. A register this structure is used by any operating system, including Unix and Windows, that are running on x86 processor. So this graph, this figure shows the typical structure of the E flag register. It includes 32 bits. Each of those bits, they have information about status flags, or it has information about some condition codes. I don't want you to memorize any of these bits, but it's beneficial. It's beneficial to look at these bits and know like well, what kind of information we're looking for in terms of interrupt enable flag, carry flags, like trap flags, especially when there's an interruption to a process. These flags are mandatory to resume the execution of a process. So if you look to the following table, you see the content and the bits associated with the E flags. They are divided into three categories. Some of them are for status flags, some of them are for control flags, some of them are even for system flags. As I said, you don't need to memorize each one of these bits separately, but it's good to know that they cover information related to state flags or control flags or even system flags. The third category to provide full control information when it comes to process control structure, knowing the location as well as the attributes, is the process control information. In the process control information, which is considered as the third majority category of information in the process control block, is the additional information needed by the operating system to control and coordinate the various active processes. So it is operating system based. So this information is different from one operating system to another based on the design of the operating system. They are mandatory just to control and coordinate the various active processes. So as we can see in this figure, the recommended structure for a process image right now, if we look at it in a virtual memory, what can we visualize the process image would be? Each process image would consist of a process control block, and in addition to a user stack, and in addition to the private address space, and space for other shared um, like shared space with other processes. In this figure, we can see that each process image would appear as a continuous range of addresses. In the actual implementation, whether it's on the main memory or even in the virtual memory, this is not the case all the time because it actually depends on the memory management scheme that is used and in the way that the control structures are organized by the operating system. But in a typical vision of the process image, it's just like a process control block, a user stack, a private address space that includes program and data, and then the shared address space with other processes. This is for each process, whether it's in the main memory or it's in the secondary memory. So as indicated in a previous table, when we talked about the process control block that include information um, about the attributes related to each process, we could actually include pointers that would allow linking of the process control block. This is mainly like if a process is running, so the process control block is created, it's saved in the memory. But when the process is in the ready state or even in the block state, we know that we are creating a ready queue versus we are, so I'm going to say this is ready queue versus we are having a blocked queue. Processes could line up in first come first serve. So this is the process control block for process one, and this is the process control block for process three. Maybe this is the process control block for process seven, while process control block for process two is stored here. And instead of using static allocation of the process control block in an array or something, it might be a good option to allow the pointers of linking the process control blocks such that the queue that we talked about it before could be implemented as a linked list, such that each process control block is linked to the next control block using pointers. So this is to represent the queue, still the blocked queue, and to represent the ready queue, but using linked list. Why we need this? Because we'd like to allow easily addition and deletion of process control blocks. When a process is created, process is deleted, process would move from one queue to another queue. So when we allow creation, deletion, and switching between processes, the process list structure using the linked list is well recommended. So to summarize the rule of the process control block, it is the most important data structure in the operating system. It contains all the information about the process that is needed by the operating system. Blocks might be read and modified by virtually every module in the operating system. And it also defines the state of the operating system. However, there is based on the fundamentals of using the process control block, they might be two important design issues. We might see a number of routines within the operating system will need access to information in the process control block. And that means the provision of direct access to these tables is somehow not difficult. So accessing is not issue. However, protection becomes an issue right now because two problems that might present themselves at this point, including if there is a bug in a single routine, such as like interrupt handler, this actually could damage the process control block, which consequently will destroy the system ability for managing the affected process. How could you protect this? That's a big challenge in designing an operating system because the process control block is the mandatory piece of information that has all the information about the process. It's easy to be accessible, but if there is a bug in a certain routine that the process control block is damaged, how would the system would perform to retrieve such image again? That's a great challenge in designing a well processor management system. Another problem is the design is change in the structure or semantic of the process control block could actually affect a number of modules in the operating system. Because of these two problems, are a big issue and a challenge in the operating system. we would like to provide better understanding and focus on how to provide protection to the process control block in order to avoid as much as we can from those problems, to maintain a trade-off between the performance issues that we might raise, to perform well protection and privacy to the data and even to the information about the processes. So it's a great task in designing operating system which should be always monitored. So before continuing with our discussion on the way in which the operating system manage processes, we need to differentiate between two modes of execution for the processor, like the processor mode of execution, normally associated with the operating system and that normally associated with user programs. Most processors, they support at least two mode of execution. Certain instructions can only be executed in less privilege mode or in more privilege mode. So the user mode is a less privilege mode, while the system mode is in the more privilege mode. So if the processor is running in the user mode, we know that we are executing less privilege instructions, while if the processor is running in the system mode, that means the processor is executing more privilege instruction. More privileged instruction could be like reading, altering a control register, like the PSW, doing some primitive I/O instructions, and even instructions that relate to memory management. In addition, certain region of memory can only be accessed in a more privileged mode. The more privileged mode, sometimes we call it control or kernel mode, and the kernel, it is mainly done on the kernel level of the operating system. So on the other hand, the user mode is where the processor is working to execute user programs. So we are not doing any kernel jobs here. We are just performing user programs, and that's why we call it less privilege mode, because user programs typically would execute in this mode, so it doesn't need a lot of privileges. While the more privileged mode is more related to the system mode, the control mode, or even the kernel mode. So if we interested to understand the functionality of the kernel, so when the processor now switches to the kernel mode or the system mode to perform functions of kernel, certain functions provided by the kernel, I would like to share with you fundamental functions that are typically found in the kernel of an operating system. First, related to process management, in which we create and terminate a process, we schedule and dispatch a process, we provide process switching, we synchronize and support inter-process communications, as well as management of the process control block. All of these are functional examples of the kernel that are maintained and processed by the processor when the processor is running in the system mode. On the other hand, a major functionality of the kernel including memory management, which performs allocation of address space to processes, swapping of processes, page and segment management. Following this, the I/O functionality of the kernel, including buffer management, allocation of I/O channels, and devices to processes. In addition to the three main tasks of project management, memory management, I/O management, the kernel also performs interrupt handling, accounting, and monitoring. So once the operating system decides, for some reason, like as we said before, the operating system would initiate a process or create a process. Now I would like to share with you the detailed description of the certain of steps that the operating system would need to do when the process is created. It can proceed as follows. First, it will assign a unique process identifier to the new process. At this time, a new entry is added to the primary process table, which contains one entry per process. Second, it will allocate space for the process, and this includes all elements of the process image. Thus, The operating system must know how much space is needed for the private user address space, including program and data, and even the user stack. These values can be assigned by default based on the type of the process, or actually they can be set based on user request at job creation time. So if the process is spawned by another process, the parent process can pass the needed value to the operating system as part of the process creation request. And if any existing address space is to be shared by this new process, the appropriate linkage must be set up. Finally, a space for a process control block must be allocated, and then a process control block is initiated. Once the process control block is initiated, the process identification portion will contain the ID of this process, plus any other appropriate IDs, such as that IDs of the parent process. And then the processor state information would typically be initiated with most entry as 0, except for the program counter, which is looking to the program entry point, and then system stack pointer, which is set to define the process stack boundaries. The process control block information portion is initialized based on standard default values plus attributes that have been requested for this process in particular. If we look to a certain example, the processor state would typically be initiated to ready, already suspended. The process state, the process that he just created, will be initiated to ready or ready suspended, and then the priority may be set by default to the lowest priority unless an explicit request is made for a higher priority. This somehow a sort of initiation to the process based on the conditions that the process has been created for. Initially, when the process is created and the process control block is initiated, the process may own no resources, including any IO or files, unless there is an explicit request for these resources from requested from the parents or even inherited from the parent process. After the process control block is initiated, we would like to set the appropriate linkages. For example, if the operating system maintains each scheduling queue as a linked list, then the new process must be put in the ready or suspended list, or the ready or even the queue list based on the conditions the process has been created for. Finally, we create or expand other data structures. For example, the operating system may maintain an accounting file on each process to be used subsequently for billing and even for performance assessment purposes. Is process always is it all about creation of a process or a termination of a process? Actually, we would like to go over interrupting a process. So we need to go over fundamentals of mechanism for interrupting the execution of processes. A process switch may occur at time that the operating system has gained control from the current running process. In this table, we have recommendations for the possible events that may give control to the operating system. Different mechanisms include interrupt, trap, supervisor call. The cause for interrupt is mainly related to external event to the execution of the current instruction. The trap is not external, is internal, and it's associated with the execution of the current instruction. Supervisor call is mainly caused by explicit request. Interrupts are used when there is a reaction to asynchronous event, external events. Trapped are related to how to handle an error or exception conditions. Supervisor call is mainly related to an explicit request or a call to the operating system function based on an explicit demand, for example, from the parent process. So if we consider system interrupts, let's actually differentiate as many systems into two kind of system interrupts. One of which we refer to it as interrupt, and the second one is the trap. Interrupts, as I said before, is mainly related to some sort of events that are external or even independent from the current running process. Like the completion of an IO operation. This was an external interrupt where the process was running, and then the completion of the IO is the IO operation is completed. So interrupt will interrupt the process, maybe to use the device or to provide to do another task. So the process will be interrupted because an external event has taken place. However, for traps, it's related to error or execution conditions, which is mainly generated within the currently running process. It could be like illegal file access attempt, as an example. If we look to ordinary interrupt control, what would happen when we look to ordinary interrupts? We know that the control will first be transferred to the interrupt handler, which will do some housekeeping and then branching into the operating system routine, which will take the full responsibility with the particular type of interrupt that has occurred. Typical interrupts that we see it as clock interrupt, IO interrupt, and memory interrupt. In clock interrupt, the operating system will determine whether the currently running process has been executing for the maximum allowable unit of time or not. This would refer to as time slice. Time slice is referred to as the maximum amount of time that a process can execute before being interrupted. If so the process has exceeded such time, this process must be switched to a ready state and another process should be dispatched. IO interrupt, the operating system um, would determine what IO action has occurred. If the IO action would constitute an event for which, for example, one or more processes are waiting, then the operating system will actually move all of the corresponding blocked processes to the ready state. That means the operating system must then decide whether to resume execution of the process currently in the running state, or even to preempt that process, to interrupt that process for a highly priority ready process. So memory fault, in the memory fault, the processor will encounter a virtual memory address reference for a word that is not actually in the memory for. So you're looking for something that is not in the memory. And that means the operating system must bring in the block or page or segment of memory containing this reference from the secondary memory to the main memory. So we are doing some IO operation right now. And this, after the IO request is issued to bring in the block of memory, the process with the memory fault is placed in a block state. This is part of memory management, which we will talk about it in more details when it comes to memory manager. And if we looking into traps, the operating system will determine that um, there is an error or exception condition that is fatal. And if so, then the current running process is moved to the exit state, and then we a process switch will definitely will occur. And if it's not fatal, then the action of the operating system will depend on the nature of the error and the design of the operating system. It may attempt some recovery procedure or simplify the user, or simply would notify the user of such fault and such error, and it may do a process switch or resume the currently running process. So it depends on the process, the operating system decision, if it's a fatal condition versus if it's not a fatal condition. So as we discussed the inclusion of an interrupt stage as part of the instruction cycle, in the interrupt stage, the processor would check to see if any interrupts are bending or not, indicated by the presence of an interrupt signal. If no interrupts are bending, that means the processor would proceed to fetch to the fetch stage, and it fetches the next structure of the current program in the current process. If an interrupt is bending, the processor does the following. It will first set the processor counter to the starting address of the interrupt handler program, and then it will switch it from the user mode to kernel mode so that the interrupt processing code. It may include any privilege instruction that will allow the processor to handle the interrupt. So this is like just a description of how the processor will switch between the modes to handle interrupts if no interrupts are bending versus if actually interrupt is bending the processor, how the processor will switch between the user mode and kernel mode to handle such interrupts. So it is clear then that the mode switch is a concept distinct from that of a process switch. A mode switch may occur without it changing the state of the process that is currently in the running state. So processor mode switch is different. The process switch between states while the processor is in either the user mode or even system mode. And in this case, the context savings and the subsequent restore involve little overhead. However, if the currently running process is to be moved to another state, like ready or blocked or suspended, then the operating system must make substantial state changes in its environment. The steps involved in a full process switch are as follows. First, the operating system will save the context of the processor, including program counter and other registers. The operating system will update the process control block of the process that is currently in running state. This included changing the state of the process to one of the other states like ready, blocked, or ready and suspended, or ready and suspended and blocked, or even exit. Other relevant fields must also be updated, including what are the main reasons for leaving the running state and accounting information. And then the operating system would need to move the process control block of this process to the appropriate queue, because now we are moving from one state to another state. So it could be ready and then it goes to blocked based on event as an example. And then the operating system will select another process for execution. And then like I would say step number 5, the operating system will update the process control block of the process that is selected. This includes changing the state of this process to running. So after this, we need to update the memory management data structure, which is actually required depending on how address translation is managed. This will be covered in memory management topic later on. And finally, we need to restore the context of the processor to that which existed at the time the selected process was actually last switched out of the running state. This could be done by loading in the previous value of the program counter and other registers. As you can see here, the process switch, which involves a state change, would require more effort than a mode switch. Now let's take a case study on the Unix SVR4. It uses the model where most of the operating system executes within the environment of a user space. There are two categories of processes in Unix SVR4, including system processes and user processes. In system processes, they are running in a kernel mode, and they are responsible of executing operating system code to perform certain administration and housekeeping functions, while user processes, they operate in a user mode to execute user programs and utilities. And they operate in kernel mode to execute an structure that might belong to the kernel. And user processes, they actually enter the kernel mode by issuing a system call. So if a user process would like to go into a kernel mode, they issue a system call when an exception is generated or even when an interrupt would occur. In Unix operating systems, in particularly the Unix SVR4, there are a total of 9 process states, including user running state, kernel running state, ready to run in memory state, asleep in memory state, ready to run in swapped state, sleepy and swapped state, emptied states, and created in zombie. It's better to understand the meaning of each of those states. Like, for example, user running means the process is in execution, but it's running on a user mode. The process in execution in a kernel mode, that means the process is kernel running. Ready to run means the process is ready to run as soon as the kernel would schedule this process for execution. Asleep in memory means the process is unable to execute until the event will occur. That means the process is main memory, but it's in a blocked state. Ready to run, the process is ready. However, the swapper must swap the process into the main memory before the kernel can actually schedule the process for execution. Sleeping and swapped, on the other hand, means that the process is waiting for an event and has been swapped to secondary memory but is still blocked. Um, Interrupted or printed procedure state means that process is returning from the kernel to user mode. However, the kernel has been has interrupted the process, and at this point a process switch will take place to schedule another process. When we say a process is created in a created state, that means a newly created process is obtained or created now, and it's ready for to be run. A zombie state, which is new, we haven't seen it before in our state diagrams. When we say a process is in the zombie state, means the process is no longer exist. However, it leaves the record for the parent's process to collect. If you look to the following diagram, it represents the state transition diagram of Unix as and a case study for us. It has two Unix sleeping states corresponding to two block states. It has the zombie state, it has the preempted state, and also it has the created state, which is done by the fork function. You could look to the different transitions between running into kernel and running into user modes. The transition between the kernel and the user mode, it's mainly based on like system call. So if there is a process in a user running, it would go to kernel running because there is a system called interrupt, and it returns back to user code when the interrupt is completed. And then you might still in the kernel mode unless the interrupt is not completed yet, or even you receive a lot of interrupts to keep you in the kernel mode. And then finally, you go into the zombie mode from the kernel. So this is the state where it only be reachable from the kernel mode. And then if you are sleeping the memory and then you swapped out, that means you are asleep and swapped out. If you have been awake, then you are in the ready to run. And then if you swapped out, if you swapped in, you will go to ready to run in memory. If you swapped out, you go back to ready to run and swapped. Initially, when the process was created, if there is enough memory, it will go immediately into ready to run in memory. If there is not enough memory, it will be ready. However, it will be run, but in a swap version. And then just like look to the transitions between those states to know exactly when two states, when a process would change its state based on a certain action that is listed on the edges of each transition. So process creation in Unix is made by means of the kernel system call, which is the fork operation. So when a process issue a fork request, the operating system will perform the following functions. First, it will allocate a slot in the process table for the new process. Then it will assign a unique process identifier to the child process. Keep in mind that a fork means a process will fork another process or multiple processes. And then third, it will make a copy of the process image of the parent with the exception of any shared memory. And after this, it would increment the counters for any files owned by the parent. The reason for this is to reflect that an additional process now also own those files. And before the last stage, it will assign the child process to the ready to run state. And then finally, it returns the ID's number of the child to the parent, because now we know that these children have been created, and then zero values to the child process. This is what the fork function would do. After the children or the process would invoke or create another process, or after the process itself is created in general, after the creation of the process, the kernel can do one of the following steps as part of the dispatcher routine. It could either stay in the parent uh, process, or it could transfer control to the child process, or could even transfer control to another process. If it stays in the parent process, that means the control will return to the user mode. This is at the point of the fork call of the parent. And if it transfer the control to the child process will begin to execute at the same point in the code as the parent process, namely the return from the fork call. If transfer control to other process, that means both parent and a child are left in the ready to run state. So when the kernel has completed these functions, it can actually create a process, and it could, after the fact, it create a process. It will stay in different processes based on what will happen after the creation. It could be staying in the parent process, or could transfer control to a child process, or could even transfer control to another process. So, summary of what has been discussed in part one of today's class. We talked about process description, including operating system control structure, process control structure, process control, including modes of operation of the processor, the process creation, and then the process switching. What are the process to switching flow or steps? We covered case study like Unix case study with focus on SVR4. We addressed the process management in this case study, including process states, process descriptions, as well as process control. Thank you for listening. And now we're going to start part two.